My name is Toni Kekez. I come from University of Split, Faculty of Civil Engineering, Architecture and Geodesy. We are a bit behind schedule, so I'll try to speed up a little bit so we don't miss our lunch break. My presentation is entitled Coastal Flood Exposure Assessment due to sea level rise and extreme wave events. This is something a bit different in comparison to other presentations, like a maybe macro scale problem comparing to, I don't know, some kind of structural masonry problems, etc., etc. So these activities are performed within PMO-GATE Interreg project that is led by Professor Nikolic. It deals with multi-hazard and multi-risk assessment activities, and activities 3.1, 3.2 are related to coastal flooding exposure assessment. Within this project, the goal is to perform a risk assessment analysis for endangered households, cultural heritage, and other assets. And one of the activities is coastal flooding risk assessment. Furthermore, one of the goals is to quantify the climate change impact and extreme waves events on the coastline. As you can see on this figure, coastal flooding can be induced by two separate natural events. One is sea level rise due to climate change, and the other one is wind-induced extreme wave events. And we'll try to follow this separately, and at the end of the presentation, make a conclusion about the combination of these two separate events. Our pilot site is city of Kaštela, one of the 7 settlements, particularly Kaštel-Kambelovac area. It is endangered by coastal flooding due to its low-lying topography. And there are a significant number of households and cultural heritage on the coastline that are potentially exposed to flooding. As you can see on the left part, on the left figure, this is a historical part of the Kaštel-Kambelovac, and on the right figure, this is the Tower of Kambi. I think it is called one of the cultural heritage assets in the Kaštel-Kambelovac area. These are some latest flooding events that occurred in Kaštela. As you can see on the left figures, these cars are flooded due to sea level rise. And on the right image, you can see some extreme waves that are flooding the coastline as well. According to the EU Floods Directive, like a key legislative document on the European level, the preparation of flood hazard and flood risk maps
and corresponding coefficients. Due to the linearity of it, we can actually rewrite it in this manner. And actually, we can observe that the only thing that we need to update is actually
someone talking.
Now coming to the numerical.
Okay. Sorry. We'll proceed. Okay. So according to the EU Floods Directive, that is a key document, legislative document on the European level, the preparation of flood hazard and flood risk maps for each flood-prone area, including coastal areas, is obligatory. And for coastal areas when an adequate level of protection is in place, the preparation of flood hazard maps shall be limited to extreme event scenarios. But this directive does not define these extreme event scenarios. They are defined by each member country independently. So we'll try to propose a methodology how to define these particular extreme event scenarios that will be applied to the Kaštel-Kambelovac area. And these scenarios can be used in order to define flood defense structures or even some kind of structural reinforcements of the existing structures. The data acquisition is related to collection of mean sea level data. That is the upper figure, that is collected on the gauging station on the Split Peninsula, and it is located 4.5 kilometers from our test site. And the second set of data is related to wind speeds and directions, and that data is collected on the wind measuring station also at the Split Peninsula for 5.2 kilometers from our test site. For our first part of the coastal flooding analysis, we separated the sea level oscillation data on two main components, and we transferred them to the frequency domain. And we identified tidal components or constituents, in total 7 of them. And we separated this measure signal into tidal effect, that is the green line, and the residual. The residual is most related to oscillations of the sea level due to changes in atmospheric pressure. And from the left figure, you can see that maximum tide is estimated as 0.28 meters above terrain elevation. And we define the residual with the probability density function in order to estimate some extreme event like a 1% exceedance probability, and it is equal to 0.3 meters above terrain elevation. Extreme sea level for current state is defined as a sum of mean sea level, tide, and selected residual level. So the mean sea level for the Castella area is 0.063 meters. As you already said, maximum tide is equal to 0.28 meters, and the residual sea level for the 1% exceedance probability scenario is 0.3 meters. So in total, that gives us the extreme event of high sea level 0.643 meters in comparison to terrain elevation. However, there are many different scenarios considering the climate change impact on the sea level, and we took one from the Intergovernmental Panel on Climate Change that defined 3 climate change scenarios for the mean sea level in Croatia. So by the year 2046, the mean sea level will rise for another 0.19 meters. By the year 2065, it will rise 0.33 meters. And by the year 2100, it will rise 0.65 meters. So when you insert these values in the beginning equation, you get that the extreme sea level value is equal to 0.833 meters for year 2046. It is equal to 0.973 meters for the year 2065 and 1.293 meters for the year 2100. The other part of the coastal flooding is related to extreme wave events that are like a separate natural hazard that is causing coastal flooding as well. Wind data is collected, as you already said, from the wind station and Split Peninsula, and wind speeds and directions are transferred to their relative frequencies. And relevant wind directions for defining coastal flood events due to extreme waves are selected according to their frequency and corresponding fetch length. Fetch length is related to the efficient length where extreme wave can develop due to blowing of the wind. And due to this criteria, if you selected the wind from the southeast that has one of the highest frequencies and one of the highest velocities on this area. Effective fetch length for the southeast direction is equal to 24.8 kilometers, and significant wave heights and wave periods are defined for the 100-year return period scenario or 1% exceedance probability scenario. And the significant wave height for the deep sea wave, where there is no interaction between wave and the sea bottom, is equal to 3.05 meters with a wave period of 6.4 seconds. However, wave that is coming towards the coastline is estimated based on the numerical model. The transformation of wave is numerically modeled in a commercial software called CG-Wave. The transformation itself is related to seafloor interaction, wave-seafloor interaction, which changes wave height, its length, direction, and its period. And you can see some images that are extracted from the model. And extreme wave height in the front of the coastline for the southeast direction is equal to 1.7 meters. So we had a deep sea wave that was 3.05 meters, and the transformation of the wave showed us that the wave on the coastline is equal to 1.7 meters. If we skip to coastal flooding assessment, then the total sea level is defined by the mean sea level, the tidal effect, the residual effect, and the wave effect at the end. So if we take this 1.7 meters and add it to these values that we already calculated for the sea level rise scenario, we can see that the total sea level for extreme flooding scenario for the year 2046 is equal to 2.533 meters. For the year 2065 is equal to 2.673 meters, and for the year 2100 is equal to 2.993 meters. If you show that on a map, on a satellite map, you can see that significant part of the historical part of the Kashta Krambelas will be flooded, and this image is only for the 2046 year scenario. So following on that, the further activities of this project are related to additional flooding scenario analysis, which are followed by the vulnerability analysis of the exposed object in order to define risk for each exposed object and develop flood risk maps. And thank you for your attention.